before continuing. Julius.
Hi. I want to talk about verification in coreboot, and it's only Lightning talk, so let's jump straight in. This is how verification in coreboot works today, and it's essentially all based on having hardware write protection on your SPI flash. So we sort of separate the SPI flash into two regions. There's a read-only region, which is permanently write protected, and then there's the rest where you can put updatable firmware. And in this read-only region, we have the coreboot boot block. So there's where execution begins. We have a CBFS with a bunch of other stages in it, and a root key which can be used to verify the read-write version and stuff like that. And so if you run this, essentially execution will start in the read-only part in the boot block and then jump to the worst stage, which is still in read-only. And then the worst stage is the code that verifies the read-write section by checking the signature, which is in the read-write part, and verifying it with that root key, which is in the read-only version. And then using the hash from that signature check to validate this read-write CBFS, which is a whole CBFS with all the other stages that you need to boot. But our current system doesn't interpret this as a CBFS, so it just essentially treats it like a blob. And the whole thing is read at once and hashed in one go, and then you continue booting from there. So you only verify as a one-shot verification at this moment, essentially. And we implicitly trust that everything in the read-only version is trusted, so there's no verification going on for those parts. And this system served us pretty well for a while, but there are some issues with it. For example, one of the problems is that we essentially end up reading all these read-write bits twice, because we read them once when we verify them at the start, but this is before DRAM is up, so at that point we can't really save them. We just hash them all and throw them away again. And then when we actually run those stages, we got to read them again. So we are wasting time reading the same bits from SPI twice, essentially. And we also have a thing called a time of check versus time of use vulnerability, which means that if you would open up the machine and, for example, desolder the SPI flash and replace it with an EM100, you could feed it back different bytes depending on which stage of execution you're in, even if it's reading the same piece on flash. So, for example, while while the worst stage is running and verifying all of this, you could feed it back the correct bytes and verification would succeed. But then afterwards, when you're actually loading the ROM stage, you could feed it back different bytes and inject malicious code. So this isn't really a problem if you just rely on SPI write protection, because in that case, if you open the case and hook up a daddy proc, you can beat it anyway. But if, for example, you wanted to extend this to Intel bootguard or a similar SoC vendor verification mechanism, then that could be a problem that you might want to defend against. And you also have the other problem with those vendor verification mechanisms, that the root of trust over there is essentially this whole block. So you would need bootcard to verify the whole read-only section, which may be very big because sometimes we have recovery code in there. And you can't really verify all the individual parts that you need to boot, because you need that boot block, you need the verse stage, you need that key, and you need a bunch of metadata that's spread around the flash and not really in one compact area that you can just cover with bootguard. So we would like to get a better system for this. And it would be great if we could somehow put the verification logic into CBFS so that every file is actually verified by the time I use it and not all in one shot. And the system we would like to implement for this somehow looks like this. So let's start with a quick refresher of how CBFS looks. It's a really simple file system. It's essentially just you put all the files one after the other, and every file has a small header which tells you the name and how long it is and a couple of other attributes. And if you look up a file in CBFS, what you do is you always start at the first file, you compare the file name, see if that's what you're looking for. If it's not, you look at the length to see where the file ends and where the next header starts, and then you look at that header and you check the name, and if it's not what you're looking for, you go to the next one and so on. And we could put a hash in those headers to hash individual files. We already have sort of that code in coreboot right now, it's just not really used. But the problem with that is that's not enough to ensure verification, because even so, essentially you got to make sure that the header you find is actually the one you were looking for. And since it does this linked list lookup through all the files until it finds the one you're looking for, you got to make sure that all those headers you go through before that are also secure. You can't just secure a single file by itself. And the way we propose to solve this is to have a master hash for the whole CBFS, which is essentially a hash of all the headers concatenated together. So the headers aren't actually concatenated on the flash. The flash layout stays the same as it is right now in the middle. But for hashing purposes, you virtually pretend as if all the headers were just concatenated, and then you calculate a hash over the whole thing. And with that system, you can do a secure file lookup, essentially the same way as before. So you start with the first file, you check if that's the file name you're looking for, but at the same time, you also throw that header into your SHA function. And then if it's not the file you're looking for, you're going to the next header, you're comparing that file name, but you also throw that header into the SHA function. And you keep walking the CBFS chain until you find the file you're looking for, but then you can't stop yet. You gotta save that header away for later, and then you still gotta keep going until you go through all the files and keep throwing all those headers into the SHA function, so that in the end you can compare this the hash that you got there with this master hash, which you gotta put in your root of trust. And at that point, you know that all the headers you just scanned were valid. And then you can go back to the header that you saved aside and use the file hash from in there to verify the data of the file you're trying to load. And in that case, you would have to verify it while you're using it. So if it's a stage, for example, you copy it into memory, then you verify it, and then you decompress it, and then you start running it. And that way you can get around these time of check versus time of use things. So let's see how that would look in practice. This still mostly looks the way it did before, but now we have this master hash, and we would embed it into the boot block program code. And that means that we can use bootguard or any other verification mechanism, even if it can only cover a single contiguous area. We just need to cover the boot block with that, and from then on we can chain into our own verification system. And when the boot block loads the verse stage, it would use that master hash to first verify all the headers in the read-only CBFS, and then use the header of the verse stage to verify the verse stage file. And for the RW side, it sort of looks the same, except that the master hash is now the hash that is verified, that is signed by vboot. So if we are booting, we still go from the boot block into the verse stage, and then the verse stage will do all the signature checks like it did before with the root key. And you can also chain the root key into that read-only CBFS to get your verification chain there. And but then after that signature check, we do not load and hash the whole RW CBFS at once. We just keep that hash in memory, and that will be our master hash for every RW CBFS file lookup later on. So then once the verse stage jumps into the ROM stage over here, it would again like check all the headers in the RW CBFS and hash them, and then use the ROM stage file hash from those headers to validate the ROM stage. And those master hashes, essentially, you would have to keep them in memory between stages so that every stage has it available to hash the next one. And with this, we can both solve the time of check versus time of use problems, except for some platform issues I'll get to in a minute. And we also solve that problem that we're loading everything twice, because now we're really only loading it when we use it and hash it at that time. So this is mostly the proposal we have. It has a few detail issues. The most important one is it works great for ARM. It has a couple of problems on Intel, because or on x86 rather, because those are executing early stages in place. And execute in place is a problem when you want to protect against time of check versus time of use, because the spy controller memory maps your code. And when you're essentially executing an instruction, the spy controller will fetch it and use it at the same time. You don't really have a spot in between where you can get in there and hash something. So this is not really a problem you can solve. I think you can try to argue about the behavior of the caches, because the spy controller usually loads it into a cache, and then if you fetch it again, it should fetch it from the cache, but that depends on the cache behavior, it depends on the exact cache lines and architecture, and the information to guarantee that you could make this work isn't really freely available, I think. So I think that is sort of a problem Intel has to solve. We sort of talked to some of the engineers about this, and they didn't have a good solution yet either, so this is an open question. On the Atom side so on the Atom CPUs, we actually already don't execute in place anymore. Instead, we load stages into cache RAM areas and then execute them explicitly from there. So in that case, that solves the problem. And on those CPUs, we should be able to support this. On the core line, for some reason, they do not support that yet, and I'm not sure why. I hope they start supporting that in the future, because then this will work. But for now, you may not be able to get full time of check versus time of use protection on those systems. If we look at performance issues, this should mostly come out either as a wash or sort of ahead of what we have right now, because you're saving all that time from not loading everything twice. But you have a little bit of extra time from doing those CBFS walks, because now you have to always walk through the whole CBFS and you can't stop at the file that you're looking for. So amortized, that would be a factor of 2 of extra bytes you need to read from SpyFlash every time you look something up. You also need to hash something, but in general, hashing times should so spy reading times should dominate hashing times, so that's probably not a big problem. And we could further solve these issues by caching the CBFS metadata once we read it. So on most platforms, you probably have enough cache RAM or SRAM available to cache those, and then we can further speed that up. So yeah, that's pretty much the idea we have right now, and it's unfortunately only an idea right now because we don't really have anyone lined up to implement it yet. But yeah, so essentially this whole idea came up from Intel trying to implement something that would support bootguard and coreboot, but it didn't solve all of these issues. So we were trying to first come up with a joint proposal that would really solve all the issues, and then now we need to find someone to implement it essentially. But maybe we'll get to that next year sometime. That's all I have. Does anyone have any questions?
Can you go back one slide?
Sure.
So you could put I mean, at the moment, you're going and reading all of the bits from the ROCBF, CBFS, all the headers. If you put all that in the boot block, then it'd be in one place and it would already be hashed, and you could just use that.
So you want to put all the CBFS metadata into the boot block, or?
You sort of said that with maybe your latest slide, but yeah. So you could do something like that, and then you wouldn't have to chase down all that data.
Right. So like one of the main goals here is to stay compatible with the old CBFS system. So if we do this, you can just disable the hashing and CBFS will look the same as it does today, and you can enable the hashing, and then it has an extra attribute, but otherwise it's the same CBFS. So all other CBFS readers don't have to be updated. Right. You could, of course, invent a whole new file system which doesn't have these issues that CBFS has, but we think with the sort of penetration that coreboot has, like sticking to the thing we already have that's already supported everywhere is a big win. So that's why we're doing this.
So why do you need to hash all headers and then to verify to read them all? Why not do like a blockchain thing? So like each next header depends on the previous one.
So you would want each header to have a hash of the next header or something like that?
Of the previous, like each header including hash, which depends on previous headers hashes, on the previous header's contents. Or like there is no field in the header for hash or something?
Well, I mean, you'd have to clarify the details, but I think that would just be less efficient in the end. Because right now, even if we have to go through all the headers on every walk, by average, you have to go through half of them, right? If you just look up a random file, it might be at the end, it might be at the beginning. So on average, you go through half of them anyway. And if you had a hash for the next header in every header, then first of all, you would have to calculate all those hashes by your walk, so you're spending extra time on that. And second of all, hashes are not that small. So the headers themselves right now are probably like, I think 40 bytes or something. And SHA-256 is 32 bytes. So we are already almost doubling the size of the header with this. And if we add yet another hash, and that's for the hashes for the files only. So if we add yet another hash to every header that's just for the previous header, then we are blowing them up even more. And then you've got to read all those extra bytes every time you walk. So I think in the end, you would come out, yeah, it wouldn't be as efficient.
Well, you can combine information. When you hash, you can combine file contents and the previous headers. So you would still have just one hash. And if you do this blockchain thing, even if files in the end of this chain are destroyed, at least the files before then, you can know that they are good. If you hash all headers together and something is corrupted somewhere, everything is lost.
Yes. I mean, we don't currently see any use cases where that corruption would be a problem, but that's true. I guess we could think about other ways to do that more efficiently. So it's an interesting thought.
For systems with boot guard, would people still be able to tinker around with their BIOSes if it's enabled?
Right, so that's of course why everyone hates bootguard, and me too. The problem is some people want to use coreboot this way, and they're going to end up implementing something, so we want to make sure they implement something that works for everyone. In the end, it always depends on what you do with bootguard, how you can use it. Normally, of course, if you, so this is only a hashing chain, there's no signatures involved, so if bootguard protects the boot block, then everything in the CBFS cannot be modified anymore. So in that case, if you're an open developer, you're screwed. But yeah, that's sort of an issue that the platform developer has to solve. Right? For example, they could release the keys to their bootguard to the owner, and then you could privately sign something else. That's sort of out of scope. We're just trying to make something that's secure, and then how you use it depends on who uses it, essentially.
Okay.
Can you move forward one page?
Forward, like this?
Yeah, this one.
Okay.
I see you have problem with the cache SRAM.
Right.
Yeah, I wonder if you use the FFCT for cache SRAM in it or use corporate version.
I don't think it makes a difference for this, but I think on all the newer chips, coreboot uses this
Because
version,
I
right?
suffered the same pain previously. We found that if we use FFCT, we need to give it the right microcore before we launch FFCT to get temporary memory in it. But the thing is, previously when I was using coreboot, we don't need to do that. We can just avoid FFCT.
Sure,
Yeah.
but you still have cache spam, right? So
Yeah.
you still have the fundamental issue.
Yeah, the thing is, Intel has the FFCT. I wonder if can have. We found Intel Fox here. Then should we get Intel Fox like can they open source FFCT? Because this is about temporary memory in it, not like for silicon in it. Then we can leverage it both ways. Because for Intel FFCT is it need a last level cache to be like permanent memory. Then for corporate version is to need the cache SRAM and just flash. I mean, enable cache SRAM only, not last level cache. Yeah, corporate has a last level cache, but it doesn't work previously.
Okay.
Yeah,
But I mean, so
there's overlap. Those two implementation are overlap together.
okay. So I think this is, to be honest, I'm not super familiar with the platform details because I mostly work on ARM systems. But as I understand, this is sort of a hardware issue. So it doesn't really
Yeah,
matter
so
whether you use
the thing is-
FFPT or corporate
Yeah, so
implementation.
I wonder if we can have some like voice on to open source FFCT. Yeah, because that one is overlap. So it's not that worthy. We spend much double effort on that.
Sure, but I don't think it would help with this problem because it's a hardware restriction.
Yeah, it's a hardware issue. Okay.
So it seems to me like you really need boot guard to verify your master hash, or someone can just replace the contents and update the hash, right?
Right.
Second thing is, does this protect against spy bus attacks? It seems like it does not.
So
Because you're verifying the hash of files as they're loaded.
okay, so first of all, so the idea is to put the master hash in the boot block. So when bootguard covers the boot block, the master hash would be in there, and so the master hash should also be covered by bootguard.
But
Otherwise,
if you're fetching things over the spy bus as
Yeah.
you're executing code, then someone could just use a spy bus attack and replace the data that you're getting, right?
right. So this is sort of, I think you're sort of getting at this execute in place problem. So first of all, if you don't execute in place, for example, if you have an ARM system which always loads code into SRAM, then this should be safe because so the first part that you're executing, the boot block, would be verified by the SOC master ROM. And then when the boot block loads the next stage, it will verify it after loading. So even if you have a spy bus attack and if you inject malicious data at any point, the verification should catch that. If you're running on an Intel system with execute in place, then you're running into exactly this issue that there's not really a way to secure execute in place systems against this unless you try to reason about
Well,
exact caching behavior.
With boot guard, it loads the.
Sorry,
it
I
loads
need
the.
to cut it here because
Okay.
time is running up.
So I'll just say BootGuard is not supposed to be susceptible to spy bus attacks, but we can talk offline about
Sure, but
how-
it relies on caching behavior that's not well documented. So but we can talk later.
All right. Thank you very much.